Hello everyone, I am Yogesh, and today in this episode we shall be decoding perhaps the very basic quantity that is all around us. We all encounter with that quantity, but yet some of us have find it really very difficult to know what exactly it is. Yes, I am talking about the motion of the bodies. See, right from a textbook placed over the table and you are pushing it, from a car that is moving with some velocity, or with a bird that is flying in the air, to the fish that is swimming. Actually, these things are really very complicated as if you look from them. But if you go by some of the very basic laws of nature, they are nothing but just like the ABCD of physics. So today, in this episode, we shall be discussing the basic laws of this nature, that is, the Newton's laws of motion. Well, before starting and going for the Newton's law of motion, I think we must take some sort of a historical leap or some recap behind what was the real story which formulated the laws of motion. Back in history, there was a very good philosopher. His name was Aristotle. Aristotle was really very keen to observe the motion of the bodies. He was really very happy to see some of the bodies moving really faster and some of the bodies moving really very slow. And so after so many observations and some thought-provoking experiments and his thinking, he said that in order to have a body in motion, one must always apply some force, that is, some external agency is either pushing it or you pulling it, and then the body comes into action, that is, the body goes for the motion. He also said that a body is always in rest. If I push the body, so the force that is exerted by me is the sole responsible of the fact that the ball or any body is moving. But perhaps after some time, Aristotle was proved to be wrong, and the basic reason behind it is what we know as the force of friction. Actually, before discussing friction in detail, we all know from our day-to-day life experiences is that even if I am able to walk on the ground, that is particularly because of there is some lagging force applied by the ground and the shoe that I am wearing. That is, the force of friction is opposing my motion. That's why I don't slip. Otherwise, if I step on a banana peel or something like that, which makes the frictional force negligible or even zero, I will simply slip and I will fall down. So what Aristotle said was partially correct, but he was somewhat wrong, because he said that okay, a body is moving, that is only because I am applying some force. But he was wrong, because he kept one thing aside, and that was he was not able to take the force of friction into consideration. For example, I will give you a very good thought-provoking experiment. You simply place some sort of book or your toy over the table, and then with your this finger you simply try to push it forward. Now if you apply a very feeble force, you will see that that particular book or the toy will not move, and after you apply certain force it will start moving. This is what Aristotle observed, but if you look down into the detail, it is only because there is some frictional force there, and that frictional force is holding the toy that you are pushing or the book that you are pushing. So what will happen is that when you apply the force lesser than the force of friction, the book or the toy will not move, and when you apply some more force, it will start moving. So I think he was deceived here, that he thought that the force is always responsible. But the guy named Galileo, he said that no, because we are all here only because of the friction. We are walking, we are sleeping, and so many things are happening like this. So since friction is there and the force that we are pushing with it, or the force that we are applying is cancelling the frictional force, that's why a body is moving. So to summarize it, a body is moving only because the force of friction gets cancelled by the force that we have applied over it. Well, after decoding the mystery behind why bodies are moving, Galileo thought that okay, now since Aristotle was wrong at some point, so I should investigate it. And through all his thinking processes and his experiments, he did a very simple experiment to explain this very basic yet very important concept. And you all can do at your home quite easily. The only thing that you require is a small pebble or a ball, and maybe a bowl, or even if you are interested in having some sort of skates that you all play in ground like this one, so you can do it anywhere. What you have to do is, suppose if I am taking a bowl, I will take a bowl like this and I will put a pebble here. Now what will you see is that the moment I left the pebble there or even the ball there, it will start moving. Okay, so it will come to the bottom of the bowl and then it will go up to the other end of it, then it will come down, then it will go to the first point where we released it, and this to and fro motion will keep on going until there is a point that the pebble will settle at the bottom of the bowl. So this was a very simple experiment. Now you replace it. You simply place some sand in the bowl. Well, not that much that it simply stops the motion of the pebble, a little bit of it. What you will see is that the to and fro motion of the pebble is obstructed. Yes, the pebble is not given a full freedom to go from this point to that point and then that point to this point. And if you are able to find out the time or the number of trips that the pebble has made in both of the cases, what you will simply find is that in case 1, when there was no medium just like sand, the pebble made more trips, but when you have put some sand into the ball, the pebble was forced to do some less trips and it came into a halt. That is because the motion was overdone. So what Galileo said was that since the pebble was at rest before I leave it in the bowl, so after I left it, it started moving, but there was some force of friction due to which the motion of the pebble was obstructed, and that's why after some time it came into rest. And then he said that since I put some sand in the bowl, what happens is that the frictional force increases. So in order to have the same number of trips that the pebble made when there was no sand in the bowl, I have to apply much more force. And I think you know the reason why, right? Because the more the sand is, the more the force you have to apply. That's why if you play in some field, like if you play a football, and if the grass is really very much there on the field, you have to kick it harder. Or if you play in rainy days and there is mud, you have to really apply a lot of force to have a ball into the goal. So this is what Galileo thought, and he showed it, that the force of friction, if it is large, you have to apply much more force to have the same effect in the absence of it. Now what we have discussed was that how Aristotle thought a process that initiated Galileo to go for a very good example and to show that how much force has to be applied if the friction is this much, or if we change the medium we have to apply a much larger force. Then after doing all this stuff, Galileo suddenly had a thought in his mind, and then he coined a very simpler term. He said that there is something called the inertia. That is, he said, every body in this universe always tries to be lazy, and it always tries to be in some sort of rest, let's say, please don't disturb me at this time. But if you apply force on that body, the body will start moving. Here is what the Galileo's concept came into act. He said that since I am applying some force on the body, and with the advent of time, what's happening is that due to the force of friction, the body is getting much less energy or much less force to keep moving. It will come to a halt. But then he said, if I have got some system, or if I can do a mechanism like this, that I can apply the same force over the period of time, then I can have that body in the state of uniform motion. Okay, so you want a better example than this one? I will give you. In our childhood days, we used to play with some tire of a bicycle. Okay, that rubber portion of it, and we will have a stick in our hand, and we will simply put it like this, and then we will hit that particular tire with our stick. And when the tire will start moving, in order to have it in a continuous motion, after every interval we will hit it, so that with us running, it also runs. So you can take that thing as an example. So what Galileo said, that these two cases, the tire being at rest, held by my hand like this, or the tire when I am having a continuous force over it, I am simply pushing it or hitting it with some stick, and then the tire comes into a sort of uniform motion. So he said that these two states, that is the state of rest and the state of uniform motion, are the same. That is, the state of inertia and the state of uniform motion are the same. I think you look a bit confused right now, and that looked to me also, because can you imagine this, that the state of rest is same as the state of uniform motion? But it is something like that. It plays with the force of friction. Okay, so first we will take the example when a body is at rest. So when the body is at rest, what happens is that no frictional force is acting. So and when you try to move the body, then only the friction will come into play. And when we go back to the our efforts to have a body in uniform motion, you are always applying the same force, so that it can cancel out the frictional force, and the body keeps on moving and moving and moving. So Galileo said that apparently it is right, because in both the cases the force of friction, it is already cancelled, so it is not more coming into play. And if the body is having some sort of non-uniform motion, so what's happening is that the force of friction is coming into act and is trying to stop the body. But in the force of uniform motion, in that case, the force is always making the body to move with a continuous effort. So that is, at every point of time, the force of friction is getting cancelled. So the state of rest or the state of uniform motion is the same. Now what we have discussed in today's episode is really very awesome. We have discussed that why some bodies tend to be in a state of rest or in some state of inertia, and why some bodies are always trying to run hard and hard with the same pace. We also discussed that what is the basic reason behind that some bodies which start their race perhaps with a greater force and with a greater enthusiasm, they end up losing all their energy and then they come into rest. Yes, we discussed about the force of friction. Why is it? Then we also decoded the mystery that Aristotle was not able to find out. That is, if a body is moving, it is not because we are applying some force into it, but actually it has to do with the force of friction that has been cancelled by the force that I have applied. Then we also discussed the Galileo's experiment of a pebble moving in a bowl, and how he showed that the greater the friction, the more the force you have to apply to have the same effects in the absence of it and in the absence of that particular, say, sand or any medium, and in the presence of sand or any medium that you can take into account. And we also discussed what exactly is inertia and how is that the state of uniform motion and the state of inertia, that is the state of rest, are one and the same. Yes, you are really right, because in this we discussed that in both the cases the frictional force is getting cancelled at every point of time. So if a body is at rest at t equal to 0, the force of friction is 0. If the body is moving, with every interval t, the force of friction is getting cancelled. Before leaving, I just want to tell you one important thing. Whenever there is some sort of acceleration or you are applying uneven force, this law does not hold that the state of uniform motion and the state of inertia is the same. In the next episodes, we shall be discussing how Newton quantified the three laws, how he came out with some new initiatives that defined the motion of the bodies.